Hello and welcome to the Pivot 2020 Geothermal Anywhere Closed Loop System session. Thank you for taking the time out of your busy schedules to listen to us today. I'm Malcolm Ross, your moderator for this session. I work at Shell in the New Energies Research and Technology team, and my title is Black Swan Detector. That title usually gets a reaction, but in this environment, I guess I won't hear it. But it pretty well describes what I do. The Shell New Energies business team decided several years ago what they were going to focus on. And focus is good, but it creates blind spots about where you're not focusing. And that's my job. Focus on the blind spots and make sure we don't get blindsided by black swan technologies. And what makes a good black swan? Innovation, of course. So it is my job to watch for innovation in areas we considered out of strategy. Geothermal is one of those out of strategy areas for topics for Shell. That's why we're here. One of the innovations I found that I believe could move the geothermal from the not as good as the other stuff we're focusing on column and into the black swan column is closed loop geothermal. And to understand closed loop geothermal systems, we're going to need to define them, describe them and all their variations, talk about their strengths and weaknesses relative to the alternatives. We're going to need to look at early test results and their economic viabilities versus with long-term thermodynamic and drilling cost models. It's worthwhile pointing out that this has been organized, this conference has been organized by the Geothermal Entrepreneurship Organization at the University of Texas, whose goal is to bring the oil and gas industry into the geothermal world as investor, partners, and developers who can operate at large scale, and to connect them with startups to innovate and fill the gaps. I think this panel personifies those goals. Every one of them represents a startup in some way, and 5 out of 6 of them have had their careers take them through the oil and gas business. So let's meet our panelists. The first panelist is Eric Van Oort. Eric is professor in petroleum engineering at University of Texas at Austin, as well as CEO of 2 startups, Evo and Spider Automation. He also spent 20 years working at Shell. Next, we have Lev Ring, CEO of the new startup called Sage System. He spent 14 years at Weatherford, ending up as director of technology, and started his career at Shell. Next, we have Joe Shearer, CEO of Greenfire, based in California, and he's the only one who doesn't have oil and gas in his pedigree. He spent 30 years as an attorney, but we won't hold that against him. Next, we have John Redfern, CEO of Ever Technologies, based in Calgary, Alberta. You have to dig deep on him, but he has the IHS Energy and Amaretta Hess in his genealogy. And our final panelist is Selena Derrick-Swiler, co-founder of Transitional Energy out of Denver, Colorado. Her roots go back through Encana and Oxy and others. It's important to note that Transitional Energy is not a closed loop company. Her group is taking a different approach that I'll let her explain. So she's here to keep the rest of us honest. So at this point, I'd like to give each of the panelists an opportunity to introduce themselves, make some introductory remarks and so on. Let's start with Eric for 2 minutes.
Okay, I'm Eric Van Oort, professor at the University of Texas in Austin, specializing in drilling and completions. I've worked for 20 years with Shell, and the great thing of working with Shell is that you get to see a lot of different wells, including very deep, high pressure, high temperature wells, which I've been involved with. And then at UT, I direct research with respect to drilling automation and well abandonment and decommissioning, which actually has a relationship with geothermal, as we will see. And then now I've been roped into looking into deep geothermal wells by Jamie Baird, a very exciting topic.
Thank you, Eric. We'll now give Lev a chance.
Yes, I'm Lev Ring. My background was in airspace engineering. I came to the oil industry 25 years ago, when my friend and business partner, Lance Cook, hired me to Shell. We developed expandable technology, set up and managed a venture, which was a joint venture between Shell and Halliburton. And then when the license was sold to Weatherford, I went there and managed global engineering and R&D for the next 15 years, mostly on drilling and well construction sites. I have been involved in some geothermal projects during these 25 years, but over the last 6 months, through multiple extensive discussions with Lance, I became very excited about potential for closed loop system. So we launched Sage Geo system. We believe we came up with a unique approach that, combined with a culture of relentless innovation and cost-cutting engineering in oil field, will allow us to drastically reduce the cost of geothermal energy.
I'll throw it to Selena now for an introduction.
Yeah, thank you, Malcolm. I think as we live through this pandemic, we're reminded that our most basic needs are food, shelter, and health, and it's nice to be in good company because we all know that in order for those needs to be met, we need reliable and affordable energy. And I think we each have a duty to find those innovative solutions and achieve those aggressive carbon reduction goals, address the climate crisis. And we really need to move as quickly as possible. As CEO and co-founder of Transitional Energy, our management team with over 7 years of experience, we're taking our knowledge and our experience from energy startups, environmental consulting, oil and gas, both conventional EOR and unconventional, as well as in mining, finance, and power marketing. And we're seeking funding to build the bridge for the energy gap between oil and gas and geothermal. Particularly as an operator. We believe there exists a unique opportunity to produce baseload power. We can extract the thermal energy from legacy uneconomic oil and gas assets, and we can utilize off-the-shelf modular power units. We basically can take the baton and build on the innovation that's come before us. There have been other oil and gas professionals, academia, and the Department of Energy have all done work in the last decade. And so we can bring that into the new decade and we can get going faster. We can reuse and recycle the existing infrastructure, assets that we already know and understand. We've identified a quicker and lower risk solution because we can eliminate all the uncertainty in the reservoir characterization, the capital intensity of drilling, and we can accelerate the payback period, so minimizing failure. I think our open loop solution is very different and perhaps on the different end of the spectrum of closed loop geothermal, but the world is really asking for our solutions to a lower carbon future, and geothermal really is a way to decarbonization. So innovation on all fronts will be required, and I really look forward to sharing ideas with others on the panel today.
Thank you very much, Selena. As you'll probably notice, we are missing 2 of our panelists. We're working now to bring them in, Joe Shearer and John Redfern. But I think we're going to move forward without them. These conferences in the age of COVID, these virtual things are always a challenge, and we're dealing with those problems now. But I'd like to go ahead and start with the panel. I'd like to ask Eric first, if you could define closed loop in your mind, and then I'm going to throw it to Ring and let him, to Lev, and let him give his view on it, and then we'll ask Selena as well. So go ahead, Eric, first, if you would do a definition.
Sure. Now, well, the people in the audience have probably heard about the EGS systems, enhanced geothermal systems, where you pump fluid through fractures, and you use that to heat up the fluid and extract energy. In a closed loop system, you pump fluid through a conduit and use the conduit to heat it up. So a well bore that could be curved back on itself, and where you do various things to maximize kind of the heating up of the fluid. Or you could think about a U-shaped well with an inlet well bore and an outlet well bore, and a deep horizontal section where your fluid heats up. So what is important to deep closed loop, or closed loop in general, is depth, which correlates with temperature. It's reservoir exposure, right? The exposure to the hot rock in order to heat up the circulating fluid, which could be water, or you could think about supercritical CO2 or so. And then lastly, it's flow rate. So how much flow can you put through that system? And that ultimately will correlate with power. So if you have these 3 things, so depth, temperature, reservoir exposure and flow rate, you can generate power in a closed loop system.
Thank you, Eric. Let's go to Lev and ask him to talk a little bit about some variations to that.
Yes, and I think we're all in this space agree that a closed loop system have two common things. One is that we moved heat exchanger for the surface downhole. Second, that we don't rely on hydrothermal resources. We just need, as Eric said, hot rock. But then implementation differs dramatically. And I see two big classes of companies or technologies that is being pursued. One is that, including our company, tries to design enclosed heat exchanger, which is not open to environment. And because it's not open to environment, then it allows to play or use multiple different heat carrying fluids. And another big class where part of the system, at least, still open to environment. And then this system mostly rely on water still as a heat carrying fluid. Thank you.
Thanks, Lev. Now, Selena, let's talk a little bit about a non-closed system. Let's talk about your system a little bit and tell us about it and how it's different from closed loop.
Yeah, so I think with the open loop system, the idea is that you're still moving fluid to the surface. So there's going to be a loss of heat by the time you get to the surface. And that's really the benefit of closed loop. If you can keep it down whole, you can capture that heat. The difference, though, with what we're doing is we're at a lower temperature for sure, so we can move the fluid and lift it to the surface and capture that thermal energy. But we don't have the high cost of drilling because we're using existing infrastructure. We don't have the technological challenge with closed loop that I think is incredible to have advancements in that area, because I could very easily see us moving our idea from open loop to closed loop. The cost of moving fluid at the surface is a high operating expense. So co-production of oil in our case is almost necessary in order to make the economics work. So I'll be looking closely at the closed loop options to see the advancement in technology and how we could apply it as we move through our company.
Thank you, Selena. Let's move on to the comparison between closed loop, which we also call Advanced Geothermal Systems, AGS, in comparison to EGS. Eric, why don't you go first again and see if you have some thoughts and comments about the differences between advanced closed loop systems and EGS, and what are their advantages and disadvantages there?
Yeah, and first of all, let me say that my perspective is that I don't want to criticize EGS, but I do want to say that it's not a good strategy to put all your eggs in one basket. And this is why people should consider kind of closed loop and open loop systems. So with EGS, as I already said, you're pumping fluid through fracture systems. So you either have to find those fracture systems or induce them through hydraulic fracturing. You have an open system, so you're open to the environment. You could pick up minerals that could scale. You could pick up gases that could lead to emissions to air. You could plug off the fracture system. If you pressurize the fracture system, you could induce seismicity, which has happened with such systems in Basel and more recently in Pohang, Korea. And of course, in the US and in Canada, kind of fracturing is kind of routinely done, but there of course are bans on fracking around the world. So there are some hurdles for the deployment of EGS. All right, and that was why it makes sense to look at deep closed loop systems, because they're able to sidestep a lot of these. As Lev already said, it's a closed loop system. We can fully enclose the fluid such that they're not in any contact with the formation. You are not pressurizing faults and running the risk of inducing seismicity, inducing earthquakes. You're not going to have emissions to air. You're not going to have issues with mineral scaling. So you're able to minimize a lot of risks. I do want to say that this is a non-trivial challenge, especially the work that I'm doing looking at deep closed loop systems. Those are not easy challenges, and we can talk about that later if there is an interest. But these are going to be difficult and large wells to drill. But it's good to look at a portfolio of different options, not just put your eggs in one basket.
Thank you, Eric. Selena, maybe you'd like to make some comments about some of those risks that Eric just mentioned, and then we'll go to Lev.
Yeah, I think that there's going to be technical challenges kind of on either side, and I really like the idea of, making sure that we think across all of the solutions. I think that fits right in line with who we are as a company, that we don't rule out a technology. We think of it in a broader sense, and how can we leverage knowledge from one area to another area, and build a successful kind of company around that. So the idea that there's work being done in AGS versus EGS, our focus is more in the sedimentary geothermal or hydrothermal kind of resource. So we are able to target a different kind of basin where we're not dealing with the natural fractures. It's kind of known injectivity and known zones. And so that higher permeability and porosity allows us to move fluid differently than in those deeper zones. And so it's maybe a different set of problem that we're looking at, but the solutions that we can look at can be very similar across the board. And so I think that's a really great point to make, is that we really shouldn't put all of our eggs in one basket and really should think about solutions in a broader sense.
Thank you, Selena. Lev, you wanted to make a remark?
Yes, I agree with Eric and Selena about everything that was said. I just want to add that I see two distinct features in closed loop system. One is that when closed loop system come to steady state, which happens in the first several days, it's going to be working this steady state for years, if not decades, okay? So that is very beneficial. All other systems are subjected to changes, environmental changes over time, but if we figure out challenges, and believe we can with closed loop system, it can work for decades. And second is, we're all talking about high cost of geothermal and being a barrier to geothermal becoming mainstream and expanding it. Well, if you're in closed loop, you're using controlling fluid. And because you're using controlled fluid, you can significantly cut cost of the top side, because you can use this fluid directly to power your turbines. That's it.
Thank you, Lev. Eric, you've been doing some thermodynamic modeling. Lev has touched now on that. Maybe you'd like to expand a little on the thermodynamic modeling you've seen and this lifetime issue and the cooling off kind of question.
Yeah, and I want to go back to something that Lev said, which I think is extremely important. If you are in hot rock and you are exposed to the hot rock, at some point you reach steady state, of course determined by the geomechanical parameters and by things like thermal conductivity of the rock. But then you could be in that state for a very, very long time, right? If you put these wells together, if you make sure that you have very good well integrity, these wells could live for a long, long time. They are not like oil and gas wells where you're on a decline curve where a reservoir declines and at some point you run out of the resource. The geothermal resource is a renewable resource. You, of course, have to model the subsurface. You have to do reservoir engineering to look at the transport of fluids, if you have a permeable zone and how this behaves in hot rock. But in principle, you have a renewable resource that could last for a very, very long time and that you could be exploiting for a long time, much longer than oil and gas wells. So that's one point. Second thing is that you probably heard about high pressure, high temperature wells that have been drilled in oil and gas. And those have been expensive wells, drilled in very challenging environments. I was involved with, for instance, the drilling of the Joseph well with Shell, which is 25,000 PSI and 250 degrees centigrade at 500 degrees Fahrenheit. And this was an expensive well to drill, but it's an offshore environment and an environment with a very narrow, what we call drilling margin, very narrow difference between pore pressure and frag rate. It's extremely difficult to operate. For these wells that we're going to be drilling in the future, we have the option to avoid those kind of environments, right? And that will dramatically impact the cost of these wells. And then, yeah, you can do the modeling on them as we have done, looking indeed at these relationships between depth and temperature, flow rate, and reservoir exposure. And the modeling looks good. I know that some people have voiced kind of hesitations against closed loop, but if you run the numbers on deep closed loop, you can get to tens of wells that generate tens of megawatts of electricity, and that is extremely exciting.
Thank you. Selena, you were nodding your head there. Did you want to make a remark about the power generation?
Yeah, I was just going to say that I think that's a really important point. It really depends on, whether these are economic or not. It's how much power can you generate from your thermal resource, and that's what you're making money off of. So I think that that modeling is really great to hear. I think we've been watching closely and working through kind of our own modeling, and it reminds me a lot of steam flooding or thermal flooding in oil and gas operations. The idea of managing that reservoir temperature and that steam bank or that hot water bank that's following the oil. And so I think we have a lot of experience to kind of transition over to this idea of geothermal and how we look at thermal resources. So it's really great to hear that information. I appreciate that.
Thank you. Let's move on now to this question that I think someone else was talking about. We don't have to put all our eggs in one basket. And I'm wondering whether the panel, and we'll start with, let's say, Lev on this one, if you see there being a mixed environment in geothermal. In the end, when we reach nirvana, will there be hydrothermal wells and sedimentary geothermal well and EGS wells and AGS wells? Or is there a natural evolution where some of these are sort of intermediate technologies and we're going to end up with one kind of geothermal that's broadly used?
Well, I don't have crystal ball, and I do believe in evolution. So evolution is going to take us wherever it's going to take us. And I do believe that there are markets and applications for all the technologies that was named. But what I want to mention that it was discussed earlier on today, this morning, that there is a significant potential market to recomplete old deep gas wells, or as Christian told this morning, hydrothermal fields that are not producing anymore or which didn't show permeability enough to be commercial. In these areas, I believe that closed loop is the only technology that can show commercial potential. Okay.
Eric, Selena, did you have a remark on that? Go ahead, Eric.
Yeah, so what Lev mentioned, kind of the repurposing of abandoned and decommissioned wells, right? That's a very fascinating proposition. I don't know if your audience knows this, but one of the biggest challenges in oil and gas is well decommissioning and abandonment. It's estimated that we might have as many as 10 million wells around the world that need to be abandoned, and it's going to cost oil and gas companies hundreds of billions of dollars to abandon this. Many companies are not properly prepared for that, right? And it's also kind of sunk cost. It's not where you get any return for your investment, right? There's no return on investment there. So if you can repurpose wells, that would be great. Now, well engineering is a very particular skill, right? We put wells together for specific purposes, right? We drill exploration wells, appraisal wells, production wells, and they're put together for a specific purpose, right? We have well integrity to consider, especially with old wells, which may have problems with well integrity and zonal isolation. And we also build them for very specific load cases, particularly production load cases. So it's not, I want to temper the expectation a bit that it's not going to be generally applicable that you can convert old wells into geothermal wells. You're also going to be probably hole size limited, right? These closed loop wells will need fairly large size bores in order to get a decent amount of throughput, and you may not have that in a well that ends up in small production casing. But you do want to look at the cases where it might be possible, right? Where you have good well integrity, where you have good zonal isolation, and where the well and the subsurface lends itself for a geothermal concept. And then it can be of course, a significant way to offset abandonment costs and actually get a return on investment. But again, it's not trivial, right? I want to temper the expectations a little bit around that.
Thank you. I'll throw to you, Lev, in just a moment, but I think one thing that hasn't been emphasized here is that closed loops aren't necessarily U or V shaped. There is also the concept of a well in well, or a tube in tube kind of configuration where you have an insulated tube inside of an existing well. So taking over an existing well, you don't have to think about, well, how am I going to intersect that with another well or whatever. You can essentially build a closed loop within a single well, which I think is an important variation, which I think is something that Lev is considering. So please go ahead and make your remark, and then maybe talk a little bit about tube in tube.
Yeah, so when I was talking about enclosed class of closed loop system, I meant tube-in-tube systems, okay? I just called it differently. Also, I want to kind of limit scope, okay? Because we cannot trick physics, okay? We still need delta T, okay? Significant delta T to make it economical. So out of millions non-producing oil and gas well, we specifically target what is called deep gas because we do need around 200 C or 400 F downhole to make it economical. But if you go to South Texas, there are thousands of these types of well. As far as challenges in recompletion, I agree with Eric, but I don't know, many people don't know, but Lance and I have been in fracking business and refracking business for the last 3 years. And if we can refrac these wells, we definitely can recomplete them to produce heat.
Thank you. Lev, let me go ahead while we have you on scope. Talk about what keeps you up at night about your particular choice of technology. What do you think is the most challenging aspect of this tube-in-tube design? You're talking about refracking, et cetera. Selena, I'm going to go to you to ask you the same question about your technology in just a minute. Mm-hmm. And Eric will, as Lev, weigh in as well. But please, Lev, go ahead. What keeps you up at night?
So I believe the challenge is common to all systems. And Eric named it, okay? It's low thermal conductivity of the formation, okay? That's what needs to be addressed, okay? And it can be addressed differently, okay? You can create a very large surface area by drilling long horizontal or directional wells, or you can pursue an approach that we are suggesting, which is we modify formation before completing well to create what we call heat root or highly thermal conductive zones, okay? And by doing it, we pretty much engineer formation to reduce thermal conductivity by relying on natural convection fractures.
So that's what keeps you up, keeping those things working. Okay, Selena, go ahead. Why don't you talk a little bit about what's keeping you up at night?
I will comment on the piece of the well bores. One of the things that we're also looking at in Colorado is there's an orphan well program where the state actually has a bunch of wells on hand that they don't know what to do with, and they need help decommissioning those assets. And so, we would really love to partner with them and bring a solution to that. But I think that wellbore integrity is a critical core part. Obviously, it's the same in oil and gas. It's the same here. So I think that's a component. What does our wellbores look like to be able to pull this fluid out and be able to pull the thermal heat off? I think the other piece is we're targeting, we think of it as a sandbox almost. So we just kind of added another wall to our sandbox. We need to look for the right reservoir that has the right characteristics with permeability and porosity, the right amount of fluid, the type of fluid that we want to move. We need to be able to have infrastructure, existing infrastructure in the local area. The power markets have to be able to be meeting this, or we have to be able to access those power markets in an economic way. So there's a lot of pieces now that we are adding to our sandbox to find the solution for. And I think that is the challenge of putting all those pieces together and getting it going when we're dealing with, hot water that cools off as we move it. So getting that heat off of it as quickly as possible is something that's a core part. And so all those pieces put together is sort of making it that step forward is the critical piece, and that is a challenge. And so leveraging everybody's knowledge and experience, I think, is what will bring success to that.
Thank you. Selena, Eric, please.
So what keeps me up at night is really excitement for this deep closed loop geothermal concept. Because the great thing is, if it can be done, it is fully globally scalable. It could be done anywhere, right? It's not dependent on particular hotspots, volcanic areas around the world. It's not just Iceland. It could be done anywhere. And if you think about the implications of that, it's mind-boggling. You could drill these wells in the middle of Austin. You could electrify grids for big cities, for major cities. The example of military bases was already mentioned earlier on. But you could do this in Africa. You could electrify Africa. You could raise billions of people out of poverty, right? The only things that have ever proven to really combat poverty is, one, the education of young women, and second, giving people access to energy, right? And so you could electrify Africa. You could do it anywhere around the globe, and that's a fascinating thing. Probably a lot of your audience was thinking about, well, how am I going to make money off this, right? And how am I going to make a lot of money off this? But think about the implications of this, right? You are able to do something fundamentally good for the planet, really leave a very positive legacy. So this is my failed attempt at trying to be inspirational, but it has really big consequences, right?
Not a failure, not at all. Thank you. Lev has a point to make.
I'm also not sleeping anymore, okay? And what is keeping me awake?
It's just age.
That I believe that closed loop technology is the only emerging method that will allow to cut capital cost below 2,000 per kilowatt, okay? Or if people live in LCOE world, then below 3 cents, okay? So that is what is so exciting. Suddenly, geothermal becomes competitive with all other alternatives.
Thank you, Lev. Good. Good. I'll move on now to the question of a real-world success. Each of you has some exposure, and I'm wondering whether, and let's go back with Lev. Do you have examples? What can you tell the potential investor in your company that you've proven, not modeled, you've proven you can show you can go do that is some of the riskier elements of what you're trying to do? What's the real world? Show me, some results.
Right. Okay, so first of all, idea is not new. As far as I know, at least the part of technology that we are pursuing was conceived by Koji Morita in mid-80s. He's from Japan, okay? And he published several papers, and then in mid-90s, he ran downhole tests in Hawaii, and then actually power plant was built in Japan. What happened was that because of low thermal conductivity of the formation, as Eric said and I said, it eventually become uneconomical, not efficient, okay? So as I said, we figure out how to overcome this challenge. The beauty of this for the investors is that it all relies on existing pieces of the puzzle. We don't need today to spend 5, 10 years and $50 million to develop new drilling or new well completion technologies. We just need to run a test and prove that it's economical, and that is very low cost investment.
Okay, thank you. Eric, do you have a comment on that?
Well, this is where we really needed the other two panelists, yeah. Right, with Greenfire and with Ivor, who are actually drilling wells right now. And it would have been nice if they could have shared some field evidence with us in that regard. I mean, I'm a technologist, I'm a scientist, right? I build models. So what I have to offer is really very state-of-the-art models, right, that are well calibrated to field cases, to thermal field cases, to demonstrate that these concepts are viable. I can't show you any wells where that have actually been drilled along the concepts. But what we're trying to do is of course entice people to get interested in it and to fund it, to be interested in it. And this is where, of course, the technology maturation cycle comes in, and the difficulty comes in talking to investors like yourself, Malcolm, like kind of black swan people that understand new technology, right, and are willing to go to bat for it in their companies to get the investment, to do some proof of concept.
Thank you. All right, let me let Lev jump in, and then I'm going to ask Selena to talk about what her best thing is for her pitching her investors. Go ahead, Lev.
Yeah, because Joe and John are not present here, I just want to compliment our potential competitors, because both their companies, Ivor and Greenfire, they are doing amazing things. They're moving very fast, and they're drilling their system, constructing their system, doing tests as we speak. And this space of technology is progressing with speed of light.
Thank you. And I will actually comment on them on their experiments for them, because I think they're crucial, and Shell helped fund them. So I feel like I have some opportunity to make some remarks about that. But let's go to Selena first, as promised, to talk about her best pitch.
Yeah, so one of the things that we have been able to benefit from is the work that's already been done for us in the last decade. So the manufacturing and the ORC units has been done, the technology's been done. In fact, Alexander Helling from Baseload Capital, who prior worked at Climon is an example of that. And so the work has been done on the technology side. Additionally, in the proof of concept, can we produce hot fluids that already exist in oil and gas basins and extract power economically from them? In the last 10 years, there's been several different deployment tests in that proof of concept space. And there's been a lot of lessons learned, things such as you can have enough flow rate, but you don't have enough temperature, or you're not able to secure a PPA because you don't have enough large scale power generation. Or, for example, early stages, they took an air conditioner, just went and bought an air conditioner from Home Depot and reversed it and tried to create power from that. So there's been a lot of like on the ground, boots on the ground work building up to this over the last 10 years. And that learning really kind of resulted. The DOE has done a lot of work and a lot of grant work and working with academia, working with oil and gas companies up in the Bakken and Williston Basin. They did one with University of North Dakota and Continental Resources, and they really put it on a source water well as what they did rather than a producing oil and gas well, but the concept is still the same. You're moving enough fluid, you can actually loop these units together in series or parallel, and so as long as you're having control of those operations, you become an operator to put all of this together. it really is economic to generate power at around 6 or 7 cents a kilowatt. So I think that that's something that's really encouraging given our knowledge of the going PPA rates for wind and solar in Colorado, averaging somewhere between 7 and 30 cents a kilowatt. So I think that the work that's been done already, we get to build off of that and go and build a commercial company off of it now.
Okay, let me now comment a little bit about two successful experiments which I helped in, at least partially. The first is the Greenfire experiment at the COSO geothermal field, where they did a tube-in-tube experiment on an existing well that was closed in because of non-condensing gases. It was completely, millions of dollars sunk to drill that well, and then they couldn't use it. So they put a vacuum insulated tube in it, and they circulated both water and supercritical CO2 as a working fluid. And they showed that they could bring that well and a large number of other wells in that field alone back online. They were sunk costs. These wells could not be used, and you can bring them online. And that was crucial for the COSO operating company, for example. They showed some critical aspects like that a thermosiphon effect happened. And what that meant was that the downgoing fluid was colder and heavier than the upgoing fluid. And so the circulation actually happens without any pumps. So that was an important thing, and they showed multiple working fluids. The other project that Shell helps with is the EVER project east of Calgary. And that project, they actually drilled, because they're going for lower enthalpy, they actually drilled what was essentially a heat exchanger in the subsurface. Two vertical wells that were about 4 kilometers apart, I believe it was, down 3 kilometers or so, and they connected them horizontally through 2 multilaterals. So what they're doing to get around the heat problem is exposing themselves to more rock by building many multilaterals in the subsurface. They're talking 12 or 15 multilaterals. So that's how they're getting exposed to more rock. They proved they can do it. They also showed the thermal siphon effect, and they have now been running for over a year, or almost a year, with the heat fitting the modeling, and the modeling shows that that will work for over 30 years. So that's two, I think, specific high enthalpy and low enthalpy experiments that showed good success. So sorry they're not here to do that. But I'll do it for them. The second thing I should mention is I know John Redfern wanted to make an offer to the community. He felt that a lot of times that we get too stuck on being competitors. And he's done stuff, as I've said, in Alberta. They're doing experiments in Norway, drilling experiments in Norway, drilling a well in Nevada this summer. He's offering opportunities to partner with other startups to bring in their technology to these sites. So you want to try a closed loop experiment, you want to try a different working fluid, go ask John, and John might let you run your fluid through his system east of Alberta. So I would encourage you to connect with John online through LinkedIn if you are interested in partnering with him in some real world opportunities to test. Okay, I think it's time for audience questions now. One of the questions that has gotten the most interest is one I think Eric perhaps wants to weigh in on, and that's what about the conductive and convective heat transport in rock? Conduction limits energy production. So it's about the heat transfer and heat transfer rates of rock and so on. If you could address that more specifically, because that's got a lot of interest.
Well, the answer to that is simple. I agree, right? It will all depend on the heat conduction characteristics of the rock, right? Will that be sufficient? Now, as I said, you can model this, right? You can model this. Actually, you can actually use some very sophisticated oil and gas modeling, some reservoir engineering modeling to do this. And we've done such modeling. We're getting ready to publish this, so all our papers right now are in peer review. But we do show that you will build up a steady state that is sufficient to extract enough heat. We've been primarily looking at hot, dry rock simulations, scenarios for this, but the simulations indicate that it is a viable concept. But yeah, the audience member who made the comment is absolutely right. This will require a strong collaboration of the disciplines, right? You can't just go and drill a well anywhere without the help of geologists and geophysicists and reservoir engineers to guide you. In geothermal well construction, I mean, well engineers will have a very important role to play, as you know, right? 40% of the cost or so is tied up in well construction, but you still would like to pick your suitable resource that has the suitable qualities.
Thank you. And Lev, you had a remark to make?
Yes, there is no question that low thermal conductivity of formation is a limiting factor. But if you imagine that we can frag down formation several thousand actually feet down, and we know how to do it, then we can create a natural convection in this fracture and bring heat from below through natural convections to the heat exchanger. And by doing this, we can artificially reduce thermal conductivity of the formation. Thank you.
Thank you. Okay, let's move quickly to Selena and talk about her system and your dependence on conduction versus convection, heat transfer questions in your open system.
Yeah, I think for us, we are going to run into the heat capacity difference of the fluids that we're moving. So the more oil we move, the less efficient we can be in terms of pulling power off, right? The heat capacity of oil is about half that of water. So we are actually looking for higher water cut wells as a result. So we view kind of the co-production of oil as sort of this skimming operation because of that. But that's a challenge. The other piece is that we leverage our knowledge in water flooding and steam flooding to think about injection patterns, right? So we're putting the water back into the rock, and we want to make sure that where we're putting it in, we can still get the same temperature coming out of the producers. So again, there's going to be modeling, right? All of this is important: the heat of the rock, the heat of the fluids. We have the capability to model, and it will take, I would agree, it takes a collaboration and a coordination between all disciplines.
Thank you, Selena. I believe, Eric, you wanted to make a comment?
No, I just wanted to add to Lev that indeed you can maybe amplify conduction from deeper zones. That's still a concept that needs to be proven, right? And you still need to find a material that has high conductivity that will work in that scenario. But this is where creativity and innovation comes in a big way, right? I think this is going to be a very fruitful area for future R&D. And a comment that I would like to make there is that people often say, this happened to me early in my career, right? That things cannot be done because we tried it 20 or 10 years ago, right? But it may be possible within the current state of the art. Things go so fast, and new concept, new innovations come along quite rapidly. And then with the right investment, who knows what is possible within 10 years, right? So don't be limited by that. I see some of that going around sometimes where people are discouraging, especially young people, saying, well, we tried that, it didn't work. But maybe it's possible right now with the current state of the art or with the right investment.
All right, thank you. I'm glad to report that John Redfern has joined us. I'm going to give him a moment to speak, give his 2-minute sort of spiel about him and his company. I see that looks like we're going to get Joe Shearer on here shortly as well. So I'll go ahead and throw here to John in just a second. But I wanted to mention to John that I did talk about your experiment east Everlight. East of Calgary, and I did actually make your pitch to share some of your resources with the community to build a sort of community effort around the some of your experimental work. But please, John, 2 minutes to talk about you and your company. Go ahead.
Got to unmute. I don't see. So yeah,
you're good.
I'm good. You can see me. Okay.
Yes.
Okay, yeah, I have no idea what everyone said. I'm assuming everyone's been talking about how wonderful. Wait, I'm still on. Can the other people on the Zoom call hang up? Yeah, okay, good. I was on 2 calls simultaneously. So I'm sure everyone's talked about how wonderful Ever is and everything else, and I have nothing more to add. I would say that it's a relief to finally be on here. The last 45 minutes have not been fun, but I've seen crisis management in action over here at Geo, so most impressive, multitasking. I think it's also impressive in another way, in that this whole thing, this whole odyssey for myself and the other founders at Ever started about 3 years ago. And I'm just tickled pink to be here with this group, because a little over 2 years ago, an early stage in our development, Geo didn't exist, but we did call up a guy named the Black Swan Detector over at Shell, our moderator, Malcolm. We said, there's a guy who should, Geo didn't exist. And we said, here's a guy who should understand what we're trying to do. And at the time, just to give a little bit of a history lesson, Malcolm sort of shooed us away. I still have his very first email. So don't get discouraged, guys, where, if you get a response like this, you got to be persistent, where he said, look, here's the 10 reasons why geothermal will never scale. And I think he used more colorful language than that, but basically that was the message. And because it's never going to scale, the oil industry will never be interested. 2 years later, here we are. So it's things have turned around in that time. And it's interesting with the progress people have been making in closed loop and other areas, that we actually can have an entire conference dedicated to the pivoting of oil and gas, technology and people and assets towards scalable, go anywhere geothermal. And so I'm good in that. It's been a great ride for us at Ever already. 2018 we did a lot of R&D. 2019 we did a demo project that answered all our early clients' questions. 2020, we're looking forward to launching our first commercial project. Everything's cooking along just fine, as we would have hoped. And again, I've done a lot of startups. It doesn't always work that way. I mean, I did 13 years of startups in China. I can tell you for sure it never always goes this way. But geothermal seems to be ripe for the start of a real long period of innovation. And we're going to need that if we're going to meet the competition. That's my 2 minutes.
Thank you, John. I wanted to let everyone know that because we've had these technical issues, we are going to let the panel run a little longer. That's going to give Joe and John a little chance to weigh in more than they've had. But let's see if we can get remarks from Joe. He seems to be online, but maybe not with video. Joe, are you there? No. Okay, well, let's keep
it. I was muted. You can hear me now?
Yeah. Yes, okay. Joe, we don't have audio, we don't have video, but please go ahead and give us a 2-minute pitch about you and your company.
Yeah, so Greenfire has been around for 7 years, but 5 years ago we pivoted from investigating an open loop geothermal approach to a closed loop approach, partly based on some work we did with Lawrence Berkeley National Labs and the potential longevity of closed loop geothermal wells. And since then, we've done extensive modeling, development, and now we're in commercial implementation of these closed loop geothermal systems, which I know, Malcolm, you like to call AGS. First, the main application we've been looking at for years is hot, dry rock power production is really the ultimate vision, but these are very large projects. And in the process we've been doing of getting recognized and involved with geothermal owners, we've been doing commercial projects with retrofits. And these are mostly in geothermal wells, but potentially in oil and gas wells, and have been looking at those as well. So indeed, our 2019 demonstration project was at Coso, California, a very large geothermal location. And that validated the modeling we've been using in all our work. It actually doubled as a retrofit example because we were able to take an unusable well and get a megawatt out of it on a continuing basis. We focused a lot on using supercritical CO2 as a working fluid, but also using water. And we tested both of those fluids as working fluids at Coso. So most recently, we've been looking at high-value industrial applications, including efficiency of mineral extraction from geothermal brine, and for hydrogen production in a more efficient method, doing it downbore using geothermal energy. And so happy to talk about those, but as for me personally, I've been 33 years as a project finance lawyer. I've been involved in all the renewable energy technologies from a financing perspective, but I like geothermal the best. So I voted with my feet and joined Greenfire.
So happy to talk about any of that some more.
Okay, thank you, Joe. And I will give you that question. One of the questions from the audience is, can you discuss the relative cost benefits ratio for the simple, straight, near vertical straw and straw kind of configuration versus U versus V in your approach for the high enthalpy, deep geothermal, high heat, high enthalpy kind of scenario? Which ones are better? Is it different in different situations, et cetera?
I suspect some of the people, I know some of the people on this panel have stood next to whiteboards as we have and come up with great configurations for wells. And two that always come up are a bore or a tube in tube approach, a coaxial concentric approach where the loop is very thin. It just goes down the bore and up the bore again, or a U loop where you can have multilaterals. And we've done extensive modeling on this, and it's really the cost benefit is just, well, it's not so much the shape of the well that determines the benefits. Instead, it's the time in residence that the working fluid is next to the hot resource. So you could take two coaxial wells, put them in a shape of two hockey sticks and have the tip of the hockey sticks together. And as long as the length of the well at temperature is the same, it doesn't really matter from a thermodynamic point of view whether you're going to make more power with two hockey sticks or two connected hockey sticks without the central chamber. Configuration is fun to talk about, but the reality is you're going to do a cost-benefit analysis based on drilling, rate of penetration, extra cost associated with completions. And one of the reasons the retrofits have worked out so well for us is that the well is already there. You don't need to modify the shape of the well at all. I see a question now. I can see you, but you can't see me.
Go ahead, Joe. I mean, Lev, go ahead, Lev. You had a remark to make?
I just wanted to comment on the cost of this new well, and that's actually what got me so excited. So when you look at this tube and tube, okay, and assuming we can solve thermal conductivity issues, then you're looking at pretty much 30% of this country at a depth 15 to 18,000 feet being at 200 plus C or 400 F temperature, okay? We definitely can drill a vertical well to this depths, okay, at around $8 million. So if I have a 9/5/8 closed loop casing, okay, and 5.5 inner tube, so the rule of thumb, even with water, 1 barrel per minute per megawatt of power. So to be commercial, I need to generate 10 megawatt of power, okay? So I need 10 barrels per minute. We definitely can pump 10 barrels per minute through 5.5 pipe. And so what happens is it immediately gives me a ballpark number of 8 million per well, 8 million for power plant, and 4 million for infrastructure, which puts any geothermal system at below 2,000 per kilowatt capital cost.
Good.
All right, thank you. Getting a lot of questions about thermodynamics. I'm going to leave that, but I do want to ask if any of the panelists, and just wave your hand if you can answer, the question about whether or not there has been any published, released economic models for the closed loop or, Selena, for your system that have a positive NPV or a low enough LCOE over the timeframes that we're talking about. So anyone have a comment about the published LCOE numbers that they're comfortable with?
Yeah, Malcolm, you're probably familiar with this, but in our demonstration at COSO, we had to do a report. It was financed by the California Energy Commission, and they were quite demanding in their report requirements. And so in addition to publishing all of the results using supercritical CO2 and water as the working fluid there, we also used the results of that demonstration to project LCOEs in various resources, including hot, dry rock. And so at the end of our report, which is downloadable from the, at the end of our, on our website, in the press relations and reports and research, you can download a paper that's quite extensive, which is our final report to the CEC, that actually provides some of that information at the end of it that goes beyond the actual demonstration results and projects those results into the future.
Thank you, Joe. Anyone else have comment on that? Otherwise, we'll move on to the next question. Eric, please go ahead. You're muted, Eric.
Sorry about that. Maybe I was expecting really facilitation for this. So a point I would like to make is point to the shale revolution. Right, when we start drilling more of these wells that are already drilled by Greenfire and EVOR and push them deeper, right? The initial cost of these wells is probably going to be high. We're probably talking tens of millions of dollars. But look at what happened in the shale revolution. Initially, when we started drilling these unconventional shale wells, these horizontal wells, they were expensive too. I've seen this close up in places like the Permian and the Haynesville and the Marcellus. What we've done then is really focus on drilling efficiency optimization, and the topic will be discussed in more detail on Thursday. But drilling efficiency optimization and just learning and applying kind of advanced machine learning and artificial intelligence techniques have taught us to really get the well cost down. And it's fair to say that if you look at how well cost for unconventional wells have come down, they've come down by an order of magnitude from the original wells that were drilled, right? To the point where actually hydraulic fracturing, completing the well, was much more expensive than actually drilling the well. And I expect that a similar thing is going to happen on more challenging geothermal wells, right? That as we drill more of them, we'll get this learning curve in place. We'll learn from it. We'll apply our techniques that we've applied in unconventionals and get the cost down.
Very good. Lev, I believe, had a remark, and then Selena.
I just wanted to mention that everybody talking about drilling cost, but as I said before, geothermal is the whole system. It's 40% drilling, 40% power plant. And we need to have more discussions about cutting costs, not only on drilling side, but on power conversion side as well.
Thank you, Selena, and then John.
Yeah, I was just going to say that, you know, the drilling costs, certainly I've seen the evolution in my own 20-year career in oil and gas of how drilling costs have changed. You know, I drilled horizontal wells back in 2005, and that changes all the way up to current present day, and I've seen that evolution happen. I think what we are looking at too at Transitional Energy is eliminating drilling costs altogether. We don't drill any wells, so if we need to add pay, we can add some pay, but it's workover costs. So you're talking about $50,000 or $100,000 on a well versus millions of dollars on a well. Additionally, we are targeting well bores where you do have larger casing and you can move 20,000 barrels of fluid, and you can rent ESPs now rather than purchasing them. So we can move a lot of fluid, and those two things really kind of change us getting started, right? The goal is to get us going, is to start building that bridge, and we need to start there. And I think that piece in trying to eliminate, when we think of like the high costs and high risk, how can we eliminate where those costs exist, or how can we reduce that? How can we reduce risk? I think that's the goal for all of us. And we approach it a little different at Transitional Energy by saying we're just not going to do drilling. We're going to find the well bores in the reservoir that we need that can move the fluid that we need to move in the markets that we can sell the power.
Thank you. John?
Yeah, I just wanted to agree with the point Eric was making, that the costs we're talking about in the early stage are not going to be our final target costs, that we're going to start at a much higher price than the local market here in North America can bear, and then we'll get down to there. But the question is not the endpoint. The question is there a route to that endpoint? Is there a route to that endpoint where we can have paying customers paying us to run down that learning curve and paying us to go through all these innovations? And that's why for ourselves, what we've done is we've searched out those resiliency markets, those remote markets, those high feed-in tariff markets, where what we're offering is enough value that even at the high starting costs, because we're not cheap to start, is enough to get us, billions of dollars worth of work that we run down that cost curve on to eventually get to where we want to go. So it's all about ultimate price and dispatchability, but it's also about a route to market.
Okay, well, let's talk about those early efforts. Right now in the US, anyways, the EGS technology is getting a lot of support, right? We just talked about the geothermal prize, and there's been all sorts of DOE funding efforts in support of EGS. Has anyone here in the panel seen support from the DOE on closed loop, the early days of closed loop? Anyone have comments about that? And by the way, Joe, I can see you now, so if you wave your hands, I know you have a response. Okay.
Good.
Anyone want to make a comment on that?
Well, if I can just blurt it out because I can't raise my hand, I guess.
No, I see you.
Yeah. Okay. Oh, you see me. Okay. Okay. So if I continue, we haven't really seen that government support for the closed loop the way we have for EGS. It was the missing chapter of the GeoVision report, I think. I'm sure it's there somewhere, but up to now, it's been pretty much an EGS world as far as government support goes. And I think that directly ties into the point I just made, is that EGS is relying on a technology that is not acceptable to the vast majority of those transitional markets, those vast majority of those early adopter markets that are really willing to pay for what we have to offer. So it's sort of two different worlds. There's an EGS world that's targeting a certain market here in the US, and there's a closed loop world that still wants to come back to the US, but wants to perfect its technology, not in Texas, but in places that will pay for it, like Germany, which is where our first commercial implementation will be.
All right, thank you, John. Joe has a remark. Please go ahead, Joe.
Well, I agree with John, and we've talked about this, but I think that while the Department of Energy seems to be so focused and has for many years on EGS, the progress is obviously very slow. And if you listened to the panel yesterday, which was a good panel, they didn't really address the fundamental issues of the political viability of a technology that is based entirely on fracking. And they addressed some and identified some of the challenges associated with a artificial reservoir creation using fracking technology and keeping them open, but those are huge challenges. Now, I would say that some of the national labs have been much more open to closed loop or AGS. And since they work very closely with the Department of Energy, I'm optimistic that there will be a change. And we've worked with some of the national labs, in fact, several of the national labs, Lawrence Livermore, Lawrence Berkeley, NREL, and Los Alamos. And there are people at those labs that will be happy to work with you. Of course, it's nice if you want to pay them as well. But
okay.
but I'm a little more optimistic that the light will go on at DOE and we'll get some support for closed loop or AGS.
Thank you, Joe. Billy Varick has a comment, and then we'll move on to another question.
Yeah, so a brief add-on. DOE, of course, has supported the creation of the GEO organization at UT Austin, and at UT we've been looking at closed loop systems. Jamie has been a strong advocate for closed loop, and we've had several engagement sessions, very good engagement sessions with ARPA-E around the concept. And I go back to what I said earlier, right? From a DOE and ARPA-E perspective, it would be good to not put your eggs in all in one basket, right? Not just focus on EGS, but look at the whole plethora of options that is available, including deep closed loop or closed loop in general.
All right. Well, on the subject of eggs in one basket, or maybe two baskets, we've been talking a lot about power here. Everyone's been mentioning LCOE and all this kind of stuff. But there are other ways to use geothermal heat. And of course, direct heat is one of them. And there has been discussion in other sessions, not so much in this session, but I think we can all agree that in some cases, direct heat to customers or even industrial processes will be useful, even with closed loop, because it's just hot fluid, whether it's water or otherwise. And so that's out there. certainly, and it may be that it's better paired with closed loop. But let me open the floor, and I'm going to start with Joe on this one. What are we missing? What are the other things that we can do with geothermal energy that we haven't been talking about?
Thanks. Well, along Greenfire's path for developing AGS technology, we kept running into other use cases, and currently we're looking at hydrogen, retrofitting geothermal on oil and gas wells, and also looking at mineral extraction and hot springs as excellent opportunities for closed loop geothermal. On the hydrogen side, hydrogen seems to be the sexiest thing in the renewable energy area these days. And what we were asked to do is to, by a strategic, is to look at whether a downbore closed loop system could actually enhance and make more efficient hydrogen production. And we looked in detail at it and found, yes, since those most hydrogen production systems rely on a lot of temperature and a lot of electricity, and since those reactions and electrolysis reactions occur more efficiently at high temperature and pressure, and since when you've made the hydrogen downbore, it's already compressed, so you don't have to recompress it at the surface. There are some inherent efficiencies for using a closed loop downbore system, with the downbore system actually being the reaction chambers for hydrogen. So we're getting a lot of interest in that. That's more of a research approach at this point. We don't have a demonstration yet, but hope to. So that's what I think is the sexiest thing in renewable now, is somehow pairing closed loop geothermal with hydrogen production, not just by making electricity and using electrolysis at the surface, but using inherent advantages. Another I've talked a little bit about retrofits, but as we were running around the world talking to folks about closed loop geothermal, almost always the first question is, well, those are big projects and that's going to take a leap of faith, but what can you do about my unproductive geothermal wells? So we're currently working on 3 continents and 3 particular projects for 3 geothermal owners looking at retrofitting geothermal wells, and indeed
I discussed that for COSO. In fact, I mentioned that already while you were out. Let me move to Lev. Lev had a point, and then I have a question for Selena. Okay.
Yeah, I just wanted to add that we specifically are looking to use closed loop or close to closed loop technology for energy storage, okay, which haven't been discussed here yet.
Another
Go ahead, Joe.
Well, another fun one, because this should always be fun, right, is looking at hot springs. And in Japan in particular, there's a huge and politically powerful hot springs industry sitting on top of fabulous geothermal resources. And we've recently been engaged by a utility research outfit and a Japanese geothermal owner to look at hot springs, because closed loop is perfect for that situation. You cannot, for a lot of reasons, just go into a hot springs area and make it a geothermal area. But with closed loop, you're not interfering with the natural production of steam for these hot spring resorts. So it surmounts both a technical challenge and a political challenge in areas that have obviously a great geothermal resource by using a closed loop system. So that one's going to be fun because we can all go to the resorts after the startup sessions.
Yeah. Selena, did you have a comment you want to make on that?
I do. I think that we look at it from an idea of a waste hierarchy. So what can we reduce, recycle, and reuse? And if we can convert our waste streams into profit streams, that's what drives kind of our business. So we think about, well, what do we produce? What do we consider waste, and how can we rethink that? And so everything from, the thermal waste of the fluids, you're actually moving fluids. So is microhydro an option? There are minerals in the fluids. Can you filter lithium and help with the battery? If we're looking at, energy independence in the US, we also approach it from kind of a lean startup model in the sense of talking to our potential customers. What do our customers actually need from us? And the utilities have said we have aggressive Renewable goals, we want to be carbon free by 2030 or 2040 or 2050. We have cities, local municipalities doing the same thing. We also in Colorado have cannabis is obviously a big industry here. So grow houses and agribusiness is a component of what we could do. And so if you start thinking about energy as a broader sort of system, you know, how can you provide solutions for that entire system? It's not that we just need to categorize ourselves, which I think humans, we like to categorize things. We like to put things in boxes. And the idea that we can be more collaborative and more cooperative and work beyond our own box, I think is really where we'll drive that innovation.
Yeah, I'm going to move to Joe, but I think I should point out one of the interesting aspects of geothermal is the ability to daisy chain these things. So in a high enthalpy solution, you can make electricity and the waste product of that is still hot enough to do a binary plant, or you can use it to do cooling, and then you can take it on and use it to do greenhouses. And now you've got multiple revenue streams where the waste of one is the input of another, and then the waste on is the input for the next. So I think that's a very promising alternative that you just don't get in a lot of other renewable power opportunities. Joe, go ahead.
Yeah, I think, Selena, thank you for mentioning the magic word there, which I think was lithium in what you mentioned. As you probably know, in California, there's huge lithium resources in the geothermal brine in the Salton Sea area. And so one of the area, which is actually a fabulous geothermal location as well. And closed loop geothermal has the advantage of being able to control two flows at once and having precise control over both the production of the geothermal brine and the heat extraction. And so what we've looked at and are continuing to talk to folks in the Salton Sea area about is using a closed loop system there to more profitably and in a more controlled fashion increase the extraction of geothermal brine for lithium, because lithium, at least in California, is the magic mineral that is going to power all of our cars, all of our everything. And so there's a big premium on lithium extraction.
Okay, thank you. I do have one other comment that maybe Selena wants to jump in on, and that is the project that actually was done in the mid-'80s, not far from here in Houston, where they drilled the a well to the Frio formation and produced 150 C water that was heavily saturated in methane. And so they split the methane and they burned the methane on top of the geothermal energy that essentially doubled the output of the plant, because you have the heat energy that you normally would do with natural gas through a natural gas turbine. And then the interesting wrinkle that they didn't try that I'd like to see done is to capture that methane that CO2 that you've created by burning that methane and putting it in the brine before you re-inject it into the earth. So you're essentially doing a carbon capture effort. And in fact, when you talk about taxation, government support, etc., you could turn this into a carbon capture project that also happens to produce geothermal and natural gas energy. So are you seeing that in your kind of project as well? Selena, is that part of your plans?
It isn't part of our plans. You know, we plan to primarily focus on oil-bearing zones versus gas-bearing zones, but we wouldn't rule it out. There's maybe some potential corrosion issues when you have a lot of water moving. So you got to pay attention to, you know, the chemistry of the fluids that you're producing. You know, that project reminds me a lot of one of the first, my first job was at Thumbs Long Beach with Oxy, and as offshore man-made islands. And back in the 30s, you know, Long Beach sank by 20, 30 feet. And so we all gathered together and said, we can't produce oil at the destruction of the environment. So how are we going to solve this problem? We brought in Disney architects to design man-made islands. We dredged up the floor of the sea floor and brought in boulders, and we built man-made islands, and we figured out how to drill wells from one location. That advanced us to pad drilling and unconventional. And what we did at Long Beach is we really focused on our operating expenses. So everything that we produce, how could we reduce the cost of producing that and generate some additional additional revenue. And so our gas wasn't worth a whole lot. It had a lot of CO2 in it, and so we couldn't sell it. So what we did, we also had rolling brownouts in California at the time, and we had 700 ESPs in the ground. So we built a power plant is what we did, and we sold our gas to our own power plant, and then the power plant, the heat, the waste stream of the heat from the power plant, we sold to the drywall company next door. So the idea that you can daisy chain, I mean, I think it's an unlimited solutions. We aren't looking at that specifically, but when the opportunity presents, yeah, absolutely, I take advantage of it.
Thank you. So we haven't heard enough from John Redfern, so we need to put John Redfern on the spot. How do you see the mix of Everloop in terms of electricity generation versus the heat generation? Can you do both? Can you vary between the two? And you might also remark about dispatchability of closed loop systems in general, and then there may be others that want to comment on the dispatchability question. But John, you want to talk about the balance between heat and electricity?
Sure. Depends on the market. Obviously, heat is something where geothermal by its very nature is more competitive. So we feel we can be competitive in that, even in North America, right from the start. Part of the problem with that is heat is a great market and a great niche market, but it's not very scalable very quickly. Electricity is the scalable market. So yes, we are exploring heat opportunities, for example, in the Netherlands, where there's a very good heat price, but not a good electricity price. But a lot of our other stuff, some of our other things are combined heat and power, like our first one in Germany. But electricity, it's the big market. It's where we want to hit the home run. It's where we're going to make a significant impact, really scale up. And if you're going to scale up with electricity, the simple fact is you got to be dispatchable now. And one of the advantages that's an inherent part of our design is its dispatchability. And when you look at, I think Jamie just published an article in Heatbeat recently that talked about that very thing and why it's important. And certainly when we go out in markets that do value the dispatchability and do price it in, it's the dispatchability itself is worth twice as much as the power. So it's 2/3 of the whole value is this on the dispatchability. We're never going to beat solar when it comes to the naked price per kilowatt hour. They've won that battle. What we got to do is win the battle on the electricity side for what is the cheapest, greenest, most efficient, most resilient form of non-intermittent green power. And that's going to take dispatchability because all the intermittents have eaten the baseload market. That's not to say there's not some baseload clients out there. We're dealing with some of them, and certainly a lot of the high feed-in tariff countries still don't price dispatchability separately. And there's lots of baseload power individual clients we can address, but in general, dispatchability is the key.
Okay, thank you. Let's give one to Lev. Question came in about the question of using high thermal conductivity materials such as graphene to transfer the heat from the subsurface instead of using fluids. And I think that's in the closed loop system, and supercritical CO2 was one of them. But I think you're talking about using high conductivity fluids in the fracs. Is that right?
That is correct. Okay, so there are multiple fluids, okay, that can be used as a working fluid, but we'll always need to remember that there is a friction, okay? We need flow rates and there is a friction, okay? So what Eric was talking about, modeling, everybody is doing modeling and balancing pretty much thermodynamics of fluids that is being used versus friction losses and other losses in the system. I was talking about using highly thermal conductive materials to create fractures in the formation going down, and by doing this cause natural convection and reduce thermal conductivity of the formation.
Excellent. Okay. I think we're going to draw a line under it here. At this point, we're already 12 minutes over the limit. John does have a comment. Let's go, and then I'll wrap up. Go ahead, John. We're having trouble with John, so we'll go to Joe.
No,
Joe?
I'm here. Sorry.
Okay.
I waited so long. No, the one thing I wanted to finish up with is that none of us really here, if we look at it, are competitors in the sense that the market potential of what we're talking about is so big that even if everyone on this panel made their upper end, sales forecast, we wouldn't be bumping heads with each other for, decades, as far as I'm concerned. So the real competition here isn't other geothermal. The real competition here isn't even wind and solar. Wind and solar, as I say, they're going to be the cheapest intermittent sources. They make a good partner for ourselves, especially if we can be reliable and even better dispatchable. So what we are in that case is on the green, when it comes to the green energy stack, we're actually competing against batteries and energy storage devices. And that's a completely different race to be won. And there is literally an avalanche of money going into energy storage. And the only way we're going to win that race is if everyone comes together. If all these startups come together with all the entrepreneurial activity and all those people partner with the oil companies to scale this rapidly and aggressively, that's the only way we're going to make that. And the other offer I'd like to put out there as part of this is we've spent about, have spent or are about to spend about $20 million setting up demo sites in Alberta, doing some development site work in Norway, drilling a well in Nevada later. If there's other startups who want to piggyback what they want to test and what they want to demo on what we're doing, it can be certainly accelerate things and make things a lot more cost effectively if we collaborate together rather than everyone having to build their own demo site from scratch. So that's something I think I can throw out there in that sort of vein.
Thank you, John. Joe gives your remark, and since Joe and John have had their opportunity, I'll go ahead and give the rest of the panelists a minute to wrap up before we shut down. So Joe, you're up.
Sure. Yeah, and really hitchhiking on what John just said, I think that closed loop geothermal crowd, and this is a good representative of it, does need to coordinate and help each other. And in that regard, I guess Greenfire is kind of the old man in the group because we've been at it for 5 years. And we've been filing a lot of patent applications, and the idea of closed loop is nothing new. On the other hand, the way you do it is there are many options. And so we've actually filed in a lot of the what we regard as the best geothermal locations in the world. And they're coming in. We're getting on average about a 1 patent granted per month at this point. So but the basic idea, and then along the way, as we were investigating, we kept running into the intellectual property rights of others who have thought about closed loop geothermal. And so we've actually, but for one reason or another, weren't able to pursue it at the time or didn't do so. So we've obtained some exclusive licenses from Blade Energy and Geotech and Gtherm for their intellectual property associated with closed loop geothermal for either oil and gas application pumping or using heat pipes or modeling techniques and that sort of thing. So in other words, this is an opportunity for us to coordinate, and we'd be happy to take anyone on this panel, but more probably others listening to this and considering geothermal through the IP landscape and work cooperatively to make AGS successful for everyone.
Thank you. Let's throw it to Selena to give her minute-long wrap-up remarks.
Yeah, I think this has been a great panel. I think it's been great to participate in, and I would definitely echo what everybody has said, is that we can work together and solve these problems together. I think that there's a lot of different ways to do innovation. There's incremental innovation or disruptive innovation, radical innovation. We take more of an architectural innovation, right? We take all the Legos apart and put them back together in a different way. And so, I think it's also important to think about who are on our teams and who are we listening to and where can we get those ideas. It goes beyond just what our experience is or what our bias is, whether I'm the only female on the panel here today, and I think that's pretty common in my industry. I'm also Alaskan Native, and that's also pretty rare in the oil and gas industry to see anybody who is kind of non-white or not fitting sort of in a box. So I think if we can be much more inclusive and broader in our sense of who are we reaching out to for these ideas, ideas and finding these solutions and thinking about innovation, because I really think it's a big challenge where it's all hands on deck for all of us to show up and help solve this problem. And I think that there's a lot of smart people out here that I'm excited to work with, and look forward to continuing that larger network.
Thank you. I'll throw it next to Lev. You have some closing remarks you'd like to make?
Yes, it was very interesting panel. I agree with everybody that field and market is big, huge. It's booming with ideas. We're all pursuing different direction, and it's exciting. And we, as John and Joe and Selena said, we are open and willing to collaborate. The only thing I would disagree with John, that battle with solar is lost. I don't think so. We're still going to fight with this target of whatever cents per LCOE, and I think we still can win this battle.
Thank you, Lev. And last remarks to Eric, and then I'm going to make some remarks.
Okay. Well, great panel. Very privileged to be participating in it. For those listening in, if this was your first exposure to closed loop geothermal wells, I hope you've seen that it's worthy of attention. That is a good alternative to EGS, and the two can live side by side. But it's definitely something that you might want to get involved in and look into. That is worthy of investment, and from my side, investment in R&D, right? It's a very fertile area. Coming from oil and gas, I see numerous opportunities to apply oil and gas learnings and technologies that can be enabling to get difficult wells drilled and to get costs down. So that is tremendously exciting, and that should basically excite any petroleum engineer as a potential whole different area of application of the skill set. So I'll leave it at that.
Thank you very much, Eric. And I want to thank all my panelists for staying with it. We had our technical challenges, but I think we got where we needed to go in the end. I really appreciate you guys taking the time to be a part of this. Thank you to our audience for staying with us while we struggled. And I want to shout out to Jamie Beard, Rob Urselman, and Alicia Williams, who were behind the scenes here today. And given the challenges we had, they worked harder than we did. So thank you very much to everyone. And I encourage you to stay with us tomorrow. We have 3 sessions tomorrow, 2 on Thursday and 2 on Friday. So still lots of good stuff to go. Lots of the questions we didn't get to will get covered in those sessions. We're also going to give the questions to my panelists today that didn't get answered, to give them a chance to answer them, and then we'll publish them. So if you didn't get your question answered, hopefully you'll see it online after this is done. So again, thanks to the panelists. Thank you to our behind the scenes people, and thanks to our listeners. Have a safe and happy rest of your day and week. Thank you very much.